We're going to work more on conversions this week, and conversions that are also like not straight up metric conversions, or not just from one unit, or like say millimeters to kilometers or something like that. So we're going to mix it up a little bit, do some problem solving conversions with a little bit more complex problems. And then you'll have some practice with each of those as well. And we're going to talk about accuracy and uncertainty. What correlates to what we'll talk about this week is the section 3 and section 4 in that first chapter of the AP Physics book. So we kind of stopped when we get right before we got to conversions last week, because that's where we kind of ended up. And again, anything we don't get to this week will be stuff that we'll work on next week, or we might get through everything. We'll see. So conversions are very helpful. We talked about all the different metric prefixes we have, quite a few. There's not a lot. Some of these are not very commonly used. You'll see a lot of ones on here that you're like, I never heard of a yoctometer or a zettameter, but some of them are more commonly used now than they used to be, because now we have terabytes and petabytes of storage, gigabytes at minimum, and we have upload speeds and download speeds of gigabytes and terabytes. So then we talk about nanotechnology, and nanotechnology has to do with things that are really small, like even a computer that's as little as 12 atoms could be used computationally, or even smaller computers, which quantum computing. So lots of more things nowadays that are at the kind of extreme edges of the metric system's measurements. And also last week, I believe we talked about our base units and derived units. We may not have gotten too far into it. So everything comes from these, and these are now defined as related to the fundamental constants of the universe. For example, time is related to the speed of light, and so is length. Length is also related to the speed of light. Things like mass or amounts of substances or currents are also related to fundamental constants, like Faraday's constant or Boltzmann's constant. These are different constants. Avogadro's constant. These are all constants that kind of seem to always be true to all of our experiences. And so we can measure these things that are always the same and relate different measurements to those. And this is kind of a recent thing. You may have learned about the metric system and saying, okay, in Paris, there's this perfectly 1 kilogram object that they keep hidden away, or there's this perfectly 1 meter long thing that they keep hidden away. But they decided to redefine constants, or redefine these measurements in terms of universal constants. Because let's say someone drops that 1 kilogram mass and it gets a little ding in it. Things can change mass over time, even if they're very well protected. So it's nice to have those based on universal constants like the speed of light. And then every other unit is derived from these fundamental base units. So derived unit, let me minimize this. I don't know what's showing on your screen. So derived units come from the base units, and these are where all of our formulas come in that we're going to learn in AP Physics 1. So all of these different units come from formulas where we're measuring something about the universe, and we derive the other units from it. For example, force is in newtons, and newtons relate to kilograms, and the acceleration of gravity, which is meters per second squared. Then energy relates to kilograms, and then another kind of iteration of that where we've got kilograms meters squared per second squared, and that's what the unit joule means. That's how it kind of gets into those fundamental units. We have some formula that takes us from and relates seconds to Webers, which is magnetic flux, to joules, which is energy, work, or amount of heat, to just seconds are related to lots of things. And then meters are related to lots of things. So coulombs, which are the amps per second or amp seconds. So lots of fundamental constants and then things we can get from those. 1/seconds is a hertz. Watts or energy per second. So lots of different time and distance and mass measurements tied into all these ideas that we're going to talk about in AP Physics 1. So when we're converting, we do need to know how things compare to one another. So how does this thing compare to another thing? You always use the value of the number in scientific or standard notation for each unit. You can do scientific notation or standard notation. It just depends on how different your units are. And your starting unit is going to be multiplied by the conversion with the unit you're coming from on the bottom and the unit you're changing it to on the top, like a fraction. And we'll do some examples of these. I'm not sure exactly how far we got last week. I don't think we got very far at all. So if we're showing something that we went over last week, then just say, okay, we did this one already. Okay, so let's say we compare something like a proton's mass. Protons are really, really small. So if a proton's mass is 1.67 times 10 to the negative 27th kilograms, very, very small, what would that be in picograms? So we have our conversion. This is the one that's on the AP Physics 1 reference table. It looks just like this. So you're not going to have all of them on the AP Physics exam. It's pretty much going to stick to ones that are on the reference table. So you won't have like zottabytes or whatever, or zottagrams or whatever. So this one, we know that a kilogram is 10 to the third grams. So if we reverse that and say how much is 1 gram to kilograms, 1 gram will be 10 to the negative third kilograms. 10 to the negative 12th grams is 1 picogram. So to kind of reverse that, 1 gram is 10 to the 12th picograms. So then I can say these two amounts are equal to one another. 10 to the negative third kilograms is equal to 10 to the 12th picograms. So 1,000th of a kilogram equals 10 to the 12th picograms. And that's what, a trillion? Yes. So to do my conversion, I'm going to put the one I'm converting to on top. So that's 10 to the 12th picograms. Then we put the one I'm converting from on the bottom. So it's 10 to the negative third kilograms. And I can use kind of the estimation thing that I did last week to kind of get this. So we're multiplying 10 to the negative 27th and 10 to the negative 12th. So that's going to be negative 27 plus 12. And then we're dividing by 10 to the negative third. So it's going to be minus negative 3 because we're dividing by it. So my answer is going to change from 1.67 times 10 to the negative 27th to 1.67 times 10 to the 15th negative 12th. And that'll be picograms. And you can also do that in your calculator like we talked about last week with E notation. So if I was doing this with E notation or using 10 raised to a power, then I'd need to make sure when I divide, I put that in parentheses. So I could put this in my calculator as 1.67 E, and I'll also on your calculator, I remember Carol didn't have the EE button, so maybe it's AXP. That could be it. So you put it as E negative 27 times 1E 12 divided by 1E negative 3. And that should give you the same answer. Or you could do 10 raised to a power. So 1.67 times 10 raised to the power of negative 27 times 1 times, or just 10. 10 raised to the power of 12. But when you do your dividing, again, make sure you do parentheses. It's not as bad for this one. But if you had a number there other than 10 to the third, and you should, again, get the same answer. So if you want to check it in your calculator real quick, go ahead. I'm going to do it in mine. Yep, I got the same answer. If you got a different answer, let me know, and we can figure out what you did wrong on your calculator. Essentially, we can use the same process to convert anything. Like, you can convert literally anything by making sure that you have the units right. And it doesn't always work out when we're doing using formulas, because we do need to use certain formulas for certain things, and they only apply in certain situations. For example, when I was doing the AP reading this summer, we had an object that was at rest, not moving, in the situation in the question I was grading, and students were trying to use formulas that had an object that was moving. And you can't use a formula with an object that's moving when the object's not moving. So that's kind of the idea. Factor label is useful 95% of the time, but sometimes you have to consider the situation and choose a formula that matches the situation. And we'll talk more about choosing formulas later on. That's a skill that we'll practice in a week or two. I think we're going to start on it next week. But if we're just converting, you just have to make sure that things are actually equivalent in that situation. And then we're going to use it the same way that we just did with the metric units. You're going to multiply your starting number by the conversion, and we're going to do it in a fraction. This is called factor label or dimensional analysis. And the fraction is going to be the two things that are equal to one another, with what the unit we're converting to on the top and the unit we're converting from on the bottom. And as long as those two things are equivalent, you can do conversions with anything. They just have to be equivalent things. So let's say that I have a Kit Kat and it has 210 calories in it, and I want to figure out how many joules of energy that is instead. Joules is the metric unit of energy, but most foods, they have their units in calories, just because calories have been used by the food industry for forever. So if we knew that 1 gram calorie is 4.184 joules, and 1 food calorie is equal to 1,000 gram calories, then we can do the conversion and figure out how many joules of energy this is. So 1 serving is 210 calories. And if we wanted to know how many joules of energy are in 1 serving, then we could just do this conversion. So each one of these is a fraction. I'm wanting to end up with joules, so I would want that on top. So 4.184 joules would be over 1 gram calorie. And then I'm starting with food calories, so that's going to be on the bottom. And I'm going to use the conversion 1,000 gram calories over 1 food calorie. Because these are actually kilocalories when you talk about how many calories are in food. Now I can do these two conversions one at a time, or I can do them both at once. Let's start out with one at a time, and then I'll show you how to do both at once. So we know here from the nutrition facts, it has 210 calories, and those are food calories. Then I'm going to use this conversion to change it to gram calories. So they'll just be 210,000. And when I divide by a conversion, this times this divided by this, then I cancel out that unit. So now my units are gram calories rather than food calories. Then if I wanted to figure out how many joules that is, I'm going to use this conversion. So 210,000 gram calories. And then it's 4.184 joules per gram calorie. So calculator for this one, 210,000 times 4.184. So when I talk about the unit of joules, you can see a joule is a pretty small amount of energy because this is 8.79 times 10 to the 9th joules. So a joule is a pretty small amount of energy. If like one Kit Kat has that 8 billion joules of energy in it. Did I do that right? Let me check my math. 210, 1, 2, 3 times 4.184 because that seems too big. Nah, it was too big. I'm like, that doesn't seem reasonable. And it was wrong. Okay, so that is 10 to the 5th. So I'm like, that shouldn't be that many powers of 10 bigger. I just multiplied it by 4. Okay. I think I put one extra zero in when I was putting in 210,000. So again, you can convert anything. You could say, okay, how many calories, how many joules is that? I could figure out pretty much any unit to any other unit as long as I have what the conversions are. And again, I did gram calories divided by gram calories, so that unit cancels out and I'm left with joules. When we're talking about, you might have seen this in the reading as you were going over it if you did the reading. So this is a nice image of the Veil Nebula, which is 110 light years across. And really pretty picture. So if it's 110 light years across. And then we talked about last week also that a meter is the distance that light travels in 1 over 300 million meter seconds. So a light year is the distance light travels in a year. So how many meters, let me move my picture, how many meters across is the Veil Nebula if it's 100 light years across? So light years distance, how many meters across is the Veil Nebula if it is 100 light years across? Okay, so let's go back to the Nearpod. And again, this one might be a little harder. And we probably need to go from seconds to years. So again, if you're not quite sure what to do on this one, I'll go over it in just a second. Give you guys a minute to few minutes to see if you can kind of figure out what equivalences you need. So 1 meter is equal to 1 over, I'm going to use just 3 times 10 to the 8th instead of this big number. Seconds. Or another way to say this is 3 times 10 to the 8th meters per second. And I'm wanting to just end up with meters, so I need to figure out how many seconds a year is. So you guys did a really good job with that. So if I've want to get rid of seconds, I need to know that 1 year is equal to 365 days, and 1 day equals 24 hours, and then 1 hour is 3,600 seconds. So several conversions there. So if I'm starting with this many meters per second, I need to just multiply these three to get how many seconds I've got. And you guys all did that correctly. So 365 times 24. And I think time is one of the most intuitive conversions that people do usually, but you guys did really well. So I got 3.15 times 10 to the 7 seconds in a year. Seconds per year. And then I also needed that this is 100 light years across. So we'll have 100 light years times 3 times 10 to the 8th. Whoops. Meters per second times 3.15 times 10 to the 7th. Running out of room here. Meters seconds per year. So then that's 100 times 3 E8 times 3.15 E7. And I got 9.45. And you might have accidentally left out the 100 light years. 9.45 times 10 to the 17th. Your number might be a little bit different if you use this number instead of 3 times 10 to the 8th. And that is meters. Yeah, you guys all did really well at figuring out that's a whole lot of seconds in a year. Okay, this was a book I read when I was a kid. You may have read it, you may not have read it. It's one of the original, there's a few people who are writing science fiction. The first were the first science fiction writers. One was Jules Verne. He was like one of the first people to write speculative science fiction. And he wrote this book called 20,000 Leagues Under the Sea. And it's about travel by submarine. And when a person does like skin diving or scuba diving, for them to surface, if they go from a deep water to the surface, the fastest they can rise and have it be safe is about 9 meters per minute. So let's say 1 league is 5.6 kilometers. So let's pretend that Captain Nemo's ship had to surface at the same speed a skin diver or scuba diver has to surface. Now, submarines are pressurized, but in this speculative fiction novel, they didn't necessarily know about pressurization, that kind of stuff. So if you had to go the same speed as a skin diver or scuba diver has to go to keep from getting the bends, how long would it take Captain Nemo's ship to surface if it could only surface at 9 meters per minute and it was 20,000 leagues under the sea? So this one's a little harder than the one previous. If I make it up, yeah, it's probably going to be harder. So I'll let you guys have a moment to try this one. So I'll pause my share. And again, the units we want to end up is seconds to surface or minutes to surface. Either one is fine. Okay, so you guys did a good job setting this up. So we've got 20,000 leagues equals the distance to surface. We've got a speed of 9 minutes equals 1 meter. Or sorry, 9 meters equals 1 minute. Then we've got kilometers to leagues. So 1 league equals 5.6 kilometers. And then we need 1,000 meters equals 1 kilometer. Okay, so these are all our conversions, and we're wanting minutes to surface. So we want minutes on top. So 1 minute, let's start with minutes then. To surface, it's to 9 meters. Doop-a-doo, undo. 1 minute is 9 meters. Then we've got 1,000 meters is 1 kilometer. Then we've got 5.6 kilometers per league. Let's do league because it's not a liter. And then we've got 20,000 leagues to the surface. Okay. So we'll end up with minutes. Meters cancels meters. Kilometers cancels kilometers. Leagues cancels leagues. Okay, so we've got most of our numbers are multiplied except for the 9. So 1 times 1,000 times 20,000 divided by 9. I got a different answer than both of you. So let me check my math real quick. 1 divided by 9 times 1,000 times 5.6. I think I missed that. Times 20,000. Okay, I got the same thing one of you got. So 1.24 times 10 to the 7th minutes to surface. And that's if you had to go at a speed that a person has to go. A person could not go 20,000 leagues under the sea, obviously. But in the science fiction novel, that's where his Captain Nemo's ship went to those great depths. Yeah, I think you both did it correctly. I think you just might have forgotten your powers of 10. The one who just put, or maybe got a little mixed up somewhere. Okay, we did that, da-da. Okay, so our next idea for today is accuracy and precision. So accuracy and precision. So precision is limited by our instruments. Like I said, now we've decided to take those standards of measurements to things that are universally constant. But like in the old days, this is old balance, they would just use something of known weight and compare it to another thing to try to get it to literally balance. That's where the word balance came from. So you have add known masses, and of course, these are subject to error because they're only so good. We have some nice mechanical balances now that have been replaced by digital scales. And digital scales can go to hundredths of a gram, thousands of the gram. I have some in my chemistry room where they'll even go to 10,000ths of a gram. But again, you have to keep the air from, the reason this is closed up is you don't want the air to blow on it because that will change it. When they're that sensitive, even the air touching it or the table being a little bit, someone leaning on a table can be enough to make it be inaccurate. So the term accuracy has to deal with how close the measurement is to the correct value of that measurement. So let's say we had a sheet of paper that was 11 inches long. Accurate measurements could be within 10% or so. So, if you had 11.1, 11.2, 10.9, those are still pretty accurate because they're really close to the true value. So precision of a measurement is how close the agreement is between repeated measurements. So looking at the range or difference between the lowest and highest values gives you the precision of an instrument. So The way GPS works is it kind of tries to locate things by using kind of this geolocation type thing. And GPS is way more accurate now than it used to be. So the black dots kind of each attempt for the satellite to pinpoint exactly where it is. They're spread out quite a lot. So this is not going to give you really good precision, but they're close to the actual location, which would give you more accuracy. If the actual location was in the middle of the bullseye, that would get you in the vicinity of it. Now, in this one, they're not close to where the actual restaurant is, but they're really close to each other. So this would be like a high precision. It's giving you something that's very close to the same thing every time, but it's not accurate because the restaurant's at the middle of the bullseye. So it's not close to where it really is. So accurate, you can think of measurement accuracy and precision as similar to this idea of the trying to get the bullseye. If you get right on the bullseye, you're both accurate and precise. If you're right around it, not the same, then you might be pretty accurate, but not quite precise. Or you could be very precise, but completely off as far as not very accurate. So when we are measuring a volume measurement, we're going to look at a couple of different measurements and look at accuracy versus precision. You do always look at the bottom of a meniscus for a graduated cylinder. The meniscus is this little dip in the water because of the water's attraction to the size of the container. The bottom of that dip is where we read a measurement for volume. So let's say that I have a person, two people getting measurements. Let's say for a person who used a 1,000 milliliter beaker, they got 450 and 450. Let's say that a person's using a 1,000 milliliter graduated cylinder instead of a beaker, and they get 495 and 505. And then person is using a flask, maybe an Erlenmeyer flask, and they got 470 and 480 for their measurements. So which one of these measurements is the most accurate? Which tool gave you the most accurate measurements? And if you just want to put it into the chat, that would be fine. Just make sure you're only chatting to me. So which tool gave us the most accurate measurements if it was from a 500 milliliter bottle of juice?